Jacob, I think you can start the class, right?
Yes.
Yeah, start the recording, please.
All right. Good evening, all.
Good evening.
Good evening, Jacob.
We are all welcome to today's class. I believe our day was well spent. So, before now, we gave 10 minutes for the others to join us so that we can start together. So, I believe, if you permit me, we can all start. Is that okay?
Yeah, yeah.
All right. Can you all see my screen?
Yes.
Okay. All right. This is probability theory and distributions, lesson 2, which is introduction to probability theory. So the instructors remains Anzaku JP, that's me, and so this is our learning outlines for this particular course. This lesson 1 and 2 we're supposed to take introduction to introduction, distributions, and some other thing that we'll be talking about. In our last class, we gave a brief introduction. We defined some terms and we gave some few examples. So today we're going to continue in the same regard. We will go on. We'll look at Bayes theorem under conditional probability. We will look at some examples under the Bayes theorem. We will talk about random variables, uh, characteristics of random variables, their uses. We will also look at probability distribution. We understand what is probability distribution and what does it mean, and we will understand more. We'll also look at what is a probability function or probability distribution function. We'll look at the definition and some few examples. We'll also look at the cumulative distribution function, otherwise called the CDF. We'll also look at the mean, that which is otherwise called expectation, and the variance. So we look at the expectation of a random variable. We'll look at some examples. Then we have summary, and then we'll have exercises. All right. As part of revision, let's do this introduction. In our last class, we said that probability theory is used for decision making and risk management in modern civilization. So if we want to take some decisive policies, and we want to see how we can manage risk, one tool that we can utilize is the probability theory. And we see that individuals use probability daily, irrespective of whether they understand the mathematical context or not. So, for instance, if a weather forecaster says that there's a 90% chance of rain, so you see people carrying umbrellas because that 90 percent chance of rain is a statement of probability. Also, if a famous stock market analyst states that there is a 90% chance or any percent chance of a severe drop in the stock market, you see people start selling their stocks because they know that any at this moment when they sell their stock, they will make more profit than when they bought them. Now also we all make decisions about the weather, our finances, and our health based on percentage statements. And these percentage statements are really probability statements. So if we're thinking about probability, we think about them in these ways, in these examples for decision making and for managing risk. Now, example in insurance. Now, in insurance,
Jacob, are you there?
from your 1 million clients just because the national rate is 15.5% claims in 100,000? Or we can equation might also arise, does the 2002 rate still apply? Now, how can you pay expenses and make a
Sorry,
profit?
Jacob, you have some network glitches. We cannot see your screen anymore. I don't know if it is from my end.
Okay, you can't see the screen? Okay, but can you hear me?
Yeah, I can hear you now, but you go off for some minutes and like you came back. I don't know. Please, can others confirm if you can see his screen?
Yes, we can. I can't see the screen anymore. The
Okay, yeah.
screen is not showing anymore.
Okay. All
Okay, do
right,
set that, please.
let me work on it. All right, can you see the screen now?
Yeah, perfect. We can see the screen now.
All right, I think it was a network glitch. All right, so we say that these are some examples that we want to look at. In 2002 in the US, deaths from motor vehicle accidents occurred at a rate of 15.5% per every 100,000 population. Now, this is really a statement of probability. Now, a mathematician will say that the probability of death from a motor vehicle accident in the next year is given by this value here, 0.000155. Now, some pertinent questions may arise. Now, we can say, should you expect exactly 155 claims from your 100,000 clients just because the national rate is 15.5 claims in 100,000? Does the 2002 rate still apply now? How can you pay expenses and make a profit in addition to paying claims? To answer these questions requires more knowledge of probability. So the knowledge of probability can be used to pool risks and to provide useful goods like insurance. So we use the knowledge of probability and probability tools widely in insurance. Uh, if you want to calculate, say, premium, claims, and so on and so forth, probability is very useful in that regard. Now, definition of terms. Though we have made all these definitions in our last class, so this is more like a revision so that we'll get more clarity even as we venture deep into the lecture proper. So last week we said that probability by counting for equally likely outcomes is defined mathematically as probability of an event equal to the number of outcomes in the event all over the total number of possible outcomes. We say this number of outcomes in an event is the event, whereas the total number of possible outcomes is what we call the sample space. Now, we also define another definition of probability. We say the first definition is the classical definition of probability, and the second definition is the relative frequency definition. In our last class, we said that the probability of an event is equal to the number of times the event occurs in n trials all over the number of uh, total sample space of the events. You see that the definition one holds for a discrete event, but immediately we take this experiment a number of times, the classical definition of probability may no longer apply. So we use the relative frequency mathematical definition of probability. So some definition of terms also and some axioms of probability. Last week, we said that for any probability to work, it must satisfy these following axioms. And we say basically there are three basic axioms of probability. Axioms means like necessary conditions for a probability to happen. And we see that the first necessary condition is that any probability of any event or the probability of any event must always be greater or equal to 0 for any event E. That is to say that there is no event that the probability is negative. So in your calculation of probability, let's say you get a negative value, then you have to check your formula and check your computation, because there's no value of probability that can be less than 0. It can either be 0 or 1, or in between 0 and 1. It cannot be more than 1. It cannot be less than 0. Also, with looking at these second axioms, we see that the probability of a sample space, or the total probability, is equal to 1. So in your calculation of probability, it cannot be more than 1. So any probability that you are calculating or computing must satisfy these three axioms. We say 1, it must be non-negative. 2, the total sample space, the probability of the total sample space is equal to 1. And then 3, we say that suppose event 1, event 2, event up to event n continually is a possibly infinite sequence. That is to say that it is uncountable of events in which each of the pair of the events is mutually exclusive. Last week, we clarified the definition of mutually exclusive. We say any event is mutually exclusive if they cannot occur simultaneously. I remember when Ilyasu gave us some differences about independence of events and mutually exclusive events. We say mutually exclusive events is when the two events cannot happen simultaneously, whereas for independent events is when the occurrence of one does not affect the occurrence of the other. Then this third axiom is telling us that if we take the probability of the union, I ranging from 1 to infinity, of all the individual events, it will give us the sum of the total probability of the events, as you can see here. So these three axioms are termed as the axioms of positivity or positiveness. So the first axiom is axiom of positiveness, that is, no probability is negative. The second axiom is an axiom of certainty, that is that no probability will be greater than 1. Or if you take the probability of the total sample space, it must always be equal to 1. And then the last axiom is the axiom of additivity or union. So if we are familiar with union of sets, we will understand this particular mathematical axiom of probability. Now, some other definition of terms. Sample space. Last week, we said that the sample space W, say W, for a probability experiment is the set of all possible outcomes of the experiment. So the set of all possible outcomes of any experiment is termed the sample space. Now, an example, if we roll a single die and the number facing up is recorded, the sample space is S equal to the set 1, 2, 3, 4, 5, and 6. We know that in a fair die, uh, it is either a 1 shows up or a 2 continually, or to 6. So there is no any number that will show up apart from these 6 numbers. So the total sample space is 1 to 6. Another example is if a coin is tossed and the side facing up is recorded, then the sample space is given by S is equal to H comma T. The set H comma T. We know that in a coin, it is either a head shows up or a tail shows up. Now, this example 3, let's see whether we can get some idea. Let's just, maybe I'll hear from you what will be the sample space. So let's look at it. Okay, the death of an insured. If an insurance company is interested in the probability that an insured will die in the next year, what will be the sample space? Let me hear from us. Are we all there? Can anyone try? Example 3. What will be the sample space if an insurance company is interested in the probability that an insured will die in the next year. What is the sample space? Can anyone try? All right. If no one will try, are we all there?
Yes, we are here.
Okay. Can we try the example tree? What will be the sample space in our
It's a
example
bit
tree?
confusing. You mentioned the property that I'm sure will die in the next year. To
Okay.
me, it's like it's a continuous sample space. I don't know if I might be. It's not discrete, or are we
It's
going to take
discrete.
it?
It's
Is it
actually
discrete?
discrete.
Is it
Yes.
day by
Let's say
day?
let's say we have an insured person. You know an insured person? A
Yeah,
person who
someone that
buys,
insured or take a particular yeah,
yeah, someone
insurance.
who buys an insurance policy.
Yeah.
So if we say we're looking for the probability that this insured person will die in the next year, what is the
So
sample
is it
space?
between 0 and 1?
Okay, no. Can you try
It's
again?
don't know.
All right, all right. So let's look at the answer. The sample space is either death or survival. Do you
I
understand
was
now?
right. I said 0 and 1. The zero is
Okay.
death and the one is life.
All right, all right. So that's nice. That's all right. That's cool. So let's continue. Okay, looking at this fourth example, uh, is an example on default of a bond. We know a bond now. Let's say uh, uh, someone buys a bond in the stock market and he fails to pay to remit. So that's default of a bond. So let's look at the example. Companies borrow money they need by issuing bonds. A bond is typically sold in $1,000 units, which have a fixed interest rate, such as 8% per year for 20 years. When you buy a bond for $1,000 unit, you are actually loaning the company your $1,000 in return for 8% interest per year. You are supposed to get your $1,000 loan back in 20 years. Now, if the company issuing the bonds has financial trouble, it may declare bankruptcy and default by failing to pay your money back. Now, investors who buy bonds wish to find the probability of default. So the sample space in this case will be default or no default. That's default, fail to pay, or no default, continuous paying. Now, definition of terms continue. Now, another term we'll consider here is compound events. That's events A or B and events A and B. So we'll see how we can differentiate these two events. Now, using the simple experiment of rolling a fair die, and suppose we have the opportunity to bet on two different events. Now, event A is an even number is rolled, and we know that the sample space of event A is either 2, 4, or 6. And then event B, a number less than 5 is rolled, and the event is a 1, 2, 3, and 4. So now let's look at this. If we bet that A or B occurs, we will win if any element of the two sets above is rolled. So probability of A or B will include it is either A or B. So we have 1, 2, 3, 4, and 6. We're not repeating any value here, as you can see. So we're not repeating any value. We have 1, 2, 3, 4, and 6. That is A or B. Now to form this set for A or B, we have to combine the sets A and B by listing all outcomes which appear in either A or B without actually repeating any of them, even if they might appear twice. Now this is also called the union of the sets in set notation. Um, I believe that we are aware of set notation. We may not wish to go deep into set notation because it's another long lecture of it on its own. Now we could also decide to bet on the event that A and B shows up. In that case, both the events E and the event F must occur on a single rule. So this can happen only if an outcome occurs, which is common to both events. So when we say A or B, we are listing all the events of A and B without repeating any outcome. But when we say A and B, we're only listing the outcomes that are in A and B. So every other outcome that is in A but not in B is not a desired outcome, or in B but not in A is not a desired outcome. But we want outcomes that are both in A and B. To form this set for A and B, we have to list all outcomes which are in both sets simultaneously. This set is referred to as the intersection of A and B in set notation. Example 5. Consider the insurance company which has written 100 individual life insurance policies and is interested in the number of claims which will occur in the next year. And this is the sample space 0, 1, 2, dot, 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 up to 100. Now, the company is interested in following two events. A, event A states that there are at most 8 claims, while event B states that the number of claims is between 5 and 12 inclusive. So, uh, if we are to list the events in A, we see that they say that there are at most 8 claims. So here are our claims. They will not be uh, more than 8. So this is the claims here. Now, and event B, they say 5 and 12 inclusive. So we have from 5 to 12 as we have here. So then events A or B and A and B are given by. So the solution to the first one, if we're interested in there are at most 8 claims and also the number of claims is between 8 and 12. If we are interested in the probability that it is either there are at most 8 claims or the number of claims is between 5 and 12, then we have A or B, which is also equal to A intersection B here, as we can see here, which will give us the set here, 0 to 12. Now, secondly, if we're interested in the intersection, that is A and B, we have the set here, 5, 6, 7, and 8. So we're only interested in the events that are in A and in B. The events A or B and A and B can also be represented using Venn diagrams. We can do that with overlapping circular regions representing A and B. Now, this is a class exercise. We may not be able to. I'll just shift it to exercise to the class exercise for our next class. That's for next week. So I'll shift this class exercise together with one other exercise which we are going to do to be submitted to be presented. We'll actually present it first and then we'll make corrections. We'll submit and we'll present. Everyone will solve the exercise, and then when we come in our next class, we'll give a few minutes for everyone to present his assignment and to explain. But remember, we need to take the assignments, attendance, and the tests we need to take them very, very important because they all form part of the continuous assessment. Now, what is an event? An event is a subset of a sample space. For instance, if a coin is tossed, we wish to find the probability of the event that's tossed a head. The sample space, that's the total sample space, is head or tail, and the event is a subset, which is the head, because we're looking for head. The probability that when you toss the coin, a head shows up. Example 7. An insurance company has sold 100 individual life policies. The company is interested in the event that at most 5 of the policies have death benefits claims in the next year. The sample space is this set, the set S equal to the set 1, 2, 3, 4 to 100. And the event E, remember we say we are looking for at most 5 of the policies. So the subset or the event is the set 0, 1, 2, 3, 4, and 5. At most means 5 and below. Then at least, for instance, if we say at most 5, we are saying that we want 5 and below. But if we say at least 5, we want 5 and above. Now, for today's class, we're going to look at conditional probability. Under that, we'll look at Bayes' theorem and its application. So, what we have done so far has formed the basis of the introduction, the definitions that we gave last week, and some examples. So, today we're going to look at conditional probability. What if there's a condition and we want to find the probability of a particular event given that another event has occurred, or there's a condition we have additional information about some other event that has already occurred? In that case, we use the conditional probability to help us ascertain the probability of what we are looking for. And then we use P, probability of B given A. So these are mathematical notation that we have here. That's the probability of P open bracket B slash A close bracket means probability of B given A. So that's what this mathematical notation means. And to denote the conditional probability of event B occurring. So given that event A has already occurred. So the following formula is provided for finding a conditional probability of event B. So here we have the formula for conditional probability. So we have probability of B given A is equal to probability of A and B over probability of A. Remember, before now, we look at probability of A and B in the example that we give above. So once we can obtain that probability, we will now use it to divide by the probability of event A. That's the additional information that we have. That's the event that has already occurred, because we are looking for a probability of B given that A has already occurred. Now, in addition to the above formal rule, there is this intuitive approach for finding a conditional probability. So what's the definition of conditional probability? The conditional probability of B given A can be found by assuming that event A has occurred, and working under that assumption, calculating that probability that event B will occur. So Bayes' theorem. So far so good. Is there any question? Is there any area we need some clarification? All right. If there's none, we can continue. Now, what's Bayes' theorem? Okay, Mrs. Sebu, can we hear your question?
It's about the assignment. I'm sorry for taking you back. The problem is the sample space. It's so confusing. Can you give
Okay,
us hints, maybe over the sample space?
okay. There's a hint on the assignment. I gave an hint. Let me go back to it. You see down there, we have a hint. We see that the sample space of interest consists of pairs which show the status of both husband and wife. So in doing that, you will first get the pair, because we're looking for total sample space. It is either death of husband or survival of husband. Then we have it is either death death of husband. Okay, sorry. It is either death of husband, then death of wife, or death of husband and survival of wife. So we pair them. The first pair will be, I'm already giving the answer. So when you pair them like that, you get the total sample space. Is that clear?
Okay, thank you. I hope so, but let's continue. Thank you.
It's all right.
Yeah.
Maybe I will shed more light when we reach the last two, when we reach the exercise session.
Okay, thank you.
You're welcome. All right, so we are here. The Bayes theorem. We extend the discussion of conditional probability to include application of Bayes theorem, or otherwise called the Bayes rule, now which we use for revising a probability value based on additional information that is later obtained. Remember, we said that conditional probability is as a result of an additional information that is given when we are looking for a particular probability, and we have an additional information, and that additional information is the fact that another event has occurred. One key to understanding the essence of Bayes' theorem is to recognize that we are dealing with sequential events. By sequential events, I mean I believe we understand what it means. Uh, Events occurring in sequence, one after the another. So whereby new additional information is obtained for a subsequent event, and that new information is used to revise the probability of the initial event. Now, in this context, the terms prior probability and posterior probability are commonly used. So, what is prior probability and what is posterior probability? Simply put, prior probability is the event that occurred before, and then posterior probability is an event that occurs after. We're looking for the probability of the event that occurs after. So, here are the definitions. A prior probability is an initial probability value originally obtained before any additional information is obtained. Whereas the posterior probability is a probability value that has been revised by using additional information that is obtained later. So the prior probability is an initial probability value obtained before, while the posterior probability is an uh, probability value that has been obtained after. Now, example 8. Let's look at this example. The Gallup organization randomly selects an adult American for a survey about credit card usage. Use subjective probabilities to estimate the following. So now we want to estimate A. What is the probability that the selected subject is male? B. After selecting a subject, it is later learned that this person was smoking a cigar during the interview. What is the probability that the selected subject is a male? And then C, which of the preceding two results is a prior probability? Which is a posterior probability? All right. So let's look at the solution. Now, you see, we know that even though here in the example, we're not giving the uh, percentage for male or female, but we know that roughly that in every population, almost half of the population is male, and approximately or estimably half of the population is female. So here in our solution, we have A. Roughly half of all Americans are males. So we estimate the probability of selecting a subject to be 0.5. I believe you understand. So we know half of 1 is 1 over 2 or 0.5. So if we estimate that the probability of selecting a male is half, then subject probability will be 0.5. Now, denoting a male by M, we can express this probability as probability of male equal to 0.5 as we have it here. Now B, want to see for B, we see that after selecting a subject, it is later learned that this person was smoking a cigar during the interview. What is the probability that the subject selected is a male? So, although some women smoke cigar, that one is true, but we know that from common knowledge, a vast majority of cigar smokers are male. So, a reasonable guess is that 85% of cigar smokers are males. So, based on this additional subsequent information, that the survey respondent was smoking a cigar, we estimate the probability of this person being a male as 0.85. So denoting a male by M and denoting a cigar smoker by C, we can express this result as follows. So we can say the probability of the subject selected smoking a cigar and is a male is 0.85. Now, for C, in part A above, the value of 0.5 is the initial probability, or otherwise called prior probability. So refer to it as the prior probability because that's the initial probability that we have. So refer to it as prior. Now, because the probability of 0.85 in part B is a revised probability based on the additional information that the survey subject was smoking a cigar, this value of 0.5 is referred to as the posterior probability. Posterior probability. I believe that example is clear. Now, what is the definition of a Bayes rule or Bayes theorem? The probability of event A, given that event B has subsequently occurred, is mathematically defined, or the Bayes theorem is given by the formula probability of A given B is equal to probability of A times probability of B given A divided by probability of A times probability of B given A plus probability of A complement. Let's take note of the complement here, times probability of B given A complement. A complement here refers to as event that is not A. So let's say, for instance, the example that we have above, we say that the probability of, let's say, male, we say is 0.5. So if we're looking for probability of female or male complement denoted by this bar, it means that we are looking for probability that they are not female. So that's opposite of, it's like the negation of a probability. We use complement as we have it here. So this formula here is called the Bayes theorem. Bayes theorem. So any question that we have that concerns the Bayes theorem, we'll use this formula for the Bayes theorem. Now, that's the formidable expression, but we will simplify its calculation. Now, see, that's the formidable expression, but we will simplify its calculation. So we see the following example, which illustrates the use of the above expression, but we can also read more on the alternative method based on a more intuitive application of Bayes theorem. So there's a more intuitive application of the Bayes theorem, but in this course, for now, maybe when we have time, we can go and read more on the intuitive application. But let's look at how we can apply this Bayes formula in addressing some conditional probabilities. So example 9. In Orange County, or just like another place, or let's say in Abuja, 51% of the adults are male, which is the prior probability. Remember, it doesn't take too much advanced mathematics to deduce that the other 49% are females. So one adult is randomly selected for a survey involving credit card usage. So here is the question now. A, find the prior probability that the person selected is a male. Then B, it is later learned that the selected survey subject was smoking a cigar. Also, 9.5% of males smoke cigars, whereas 1.7% of females smoke cigars. So this data is based on the Substance Abuse and Mental Health Service Administration data. Now, so we want to use this additional information to find the probability that the selected subject is male. So using the formula of the Bayes theorem, but before then, let's define some terms, some notation. So we use M for male. We use so M here for male, and then we use M complement for female, that is, or not male. We know we have male and female. So and then we have C here for female, for cigar smokers, and then C bar here for not a cigar smoker. Now, before using the information given in Part B, we know that only 51% of the adults in Orange County are males. So the probability of randomly selecting an adult and getting a male is given by probability of males equal to 0.51. So that's the prior probability. So I've solved A. Then for B, based on the additional information that is given, we have the following information. We have that first, the prior probability, that probability of males in that county is 0.51%, that is 51% of the adults are males. Secondly, we have a probability of females or not males here to be equal to 0.5 if you subtract 0.51 from 1. Now also, because 49% of the adults are females. Now here we have the conditional probability that that's probability that the person speaking at random smokes a cigar, given that is a male, is equal to 0.095, because 9% of the males smoke cigar. We got it from the additional information. That is, the probability of getting someone who smokes cigars, given that the person is a male, is 0.095. Then here we have probability that the person that smokes the person picking at random smokes a cigar, given that it's not a male, sorry, given that it's not a male, or given that it's a female, is 0.017, because 1.7% of the females smoke cigars. That is, the probability of getting someone who smokes cigars, given that the person is a female, is 0.017. Now, so let's apply the Bayes theorem, that is the formula of the Bayes theorem, to get what we're looking for. So the probability of picking someone who smokes cigar, given that is a male, is given by the formula here. Remember the Bayes theorem formula we gave above, and if we substitute A and B, the formula initially carried A and B, but if we substitute it with the variables that we have in this particular question, we have probability of M given C, that is probability that we're picking a male, given that he smokes cigar, is equal to probability of P of probability of male times probability of that the person smokes a cigar, given that he's a male, all over the probability that the person is a male times the probability that the person smokes cigar, given that he's a male, plus the probability that the person is a female, multiplied by the probability that the person smokes cigar, given that he's a female. So substituting our values that we have here, we have that we have 0.51, which is the probability that the probability of male, times the prior probability that the person smokes cigar, given that is a male, all over the probability that the person is a male, multiply the probability that the person smokes a cigar, given that is a male, plus the probability that the person is a female, multiply by the probability that the person smokes a cigar, given that is a female. We'll get this. And when we multiply the two of them, when we do the computation, when we compute this value using our calculator, we get 0.85329341. And when we round it to three decimal places, we have 0.853 as the answer. Now, so this is a brief explanation to example 9. Now, before we knew that the survey subject smoked a cigar, there was a prior probability that that's 51% were male. That's 0.51 probability that the survey subject is a male. because 51% of the adults in Orange County are males. Remember, we said that's the prior probability. However, after learning that the subject smoked a cigar, we revised the probability to 0.853. Now, there is a 0.853 probability that the cigar smoking respondent is a male. This makes sense because the likelihood of a male increases dramatically with the additional information that the subject smokes cigars because so many more males smoke cigars than females. So you see, using applying the Bayes theorem, it gives us uh, an answer which is approximate to that which we approximated in our first example. So we see that the Bayes theorem can help us to estimate a conditional probability. Now, exercise one. So we will solve this exercise together with the exercise we gave uh, earlier on. So this exercise. In Orange County, 51% of the adults are males. One adult is randomly selected for a survey involving credit card usage. Now, A, find the prior probability that the selected person is female. Then B, it is later learned that the selected survey subject was smoking a cigar. Also, 9.5% of males smoke cigars, whereas 1.7% of females smoke cigars, based on the data from the substance abuse and mental health services. Now, use this additional information to find the probability that the selected subject is a female. So we will solve this with the other example and we'll present in our next class. All right. Is there any question so far or addition? All right. If there's none, let's forge ahead. All right. So we'll look at random variables uh, and we'll understand what a random variable is. So before we get to define a random variable, let's look at this example. Now, when we select items at random from a batch of size n until the first defective item is found, and we record the number of non-defective items, our sample space will be uh, S equal to the set 0, 1, 2, continually to n. So we'll keep on repeating that experiment until the first defective item is found. So let's say we do the experiment once, we select the items 1, and we did not find a defective item. We'll repeat it again, and then we'll do that again. We'll do that again. Then we will stop until the first defective item is found. So we'll do that n times, and that will be our sample space 0, 1, 2, continually to n. Now the result from the experiment becomes a variable. It becomes a variable because we don't know uh, what we're going to get, and we're taking this at random. So that is a quantity taking different values on different occasions. So because we don't know whether at the first selection we will get a defective item, or at the second selection, or at the third selection. So we are doing this experiment randomly, and we have no idea which value this outcome will be, and that is why it's a variable. So we are doing it randomly. So we say we call such an experiment a random variable. So we call it a random variable because the experiment involves selection at random, and we call it that's why we call it a random variable. Now it is usually abbreviated by RV, and it is denoted by capital letter X. So anywhere we see R dot V, small letter RV, we're talking about random variable. And anywhere you see a capital letter X, it is a random variable. Now, some definitions about a random variable. So what is the range of a random variable? The range of a random variable is a set of all possible values that a random variable X can take. We call that the range of X. So the set of all possible values, or otherwise the sample space of a random variable, is called the range of that random variable. Now we also have a discrete random variable and we have a continuous random variable. Now what is a discrete random variable? A random variable, say x, is a set is said to be discrete if its range consists of a finite or a countable number of values. So if the range of a random variable is countable or is finite, then we call it a discrete random variable. Now an example. Now let's look at our simple example of tossing a coin repeatedly. Now number of heads, that's heads that will show up in the first 5 tosses. It may be that the head shows up at the first, or it may be that no head shows, or the head shows up at the first toss, or head shows up at the second toss, or head shows up at the fifth toss. So then the number of tail before the first head can either be 0 or 1 or 2 or continually. So now let's note that although the definition of a discrete random variables allow random variable allows it to take any finite or countable set of values, the values are in practice almost always integers. By integers, we mean they don't have, let's say, they don't, now, uh, by integer, we mean they don't have point. Let's say we have numbers like 2, we say this is an integer, or 3, or any number that is that maybe 25, 30, insofar as it does not have point. So we say discrete. That's in practice. That's what we actually mean when we are talking about integers. But when we have, let's say, 2 point something, 2.1 for instance, so this is no longer discrete. It becomes a continuous random variable. So that's what we usually actually use in practice. Now, a continuous random variable is said to be a random variable is said to be continuous if its CDF is a continuous function. So we see that later. We'll see more on discrete random variable and continuous random variable. So we will understand more on the behavior of a random variable, and once we understand the behavior of a random variable, we'll be able to categorize this behavior under a discrete random variable or a continuous random variable. So we have different discrete random variables or discrete probability distributions and so on and so forth. So we'll explain more as we delve more and more into the class. All right, probability distributions. Now we're getting more and more gradually into the crux of our lecture. Remember, this class is probability theory and distributions. So, what is a probability distribution? Oftentimes, when we hear of probability distributions, mathematically, our mind comes to different types of distribution, maybe some formulas like normal distribution, uh, binomial distribution, Poisson distribution, geometric distribution, and so on and so forth. But what actually is a probability distribution? So that we can understand in simple terms, so that as we start dealing with mathematical equations and formulas, for us, that's the CDF and PDF of different distributions, we'll be able to understand that this is actually what we are doing, so that it will make more sense and make more meaning, because we need to understand them more practically. Now, in simple terms, probability distribution means how to describe the behavior of a random variable. Remember, we see a random variable is a random event. And we see that for us to describe the behavior of a random variable, we need the understanding of probability distributions. So probability distributions simply means how a random variable behaves. how a random variable behaves. For instance, if we are looking at the tossing of a fair die, or in our example of insurance of a couple, uh, or we say the insurance, if we remember when we are talking about the sample space of an insured person, whether he will die the next year or not, in that example. So we say that the sample space is either the person dies, uh, which is 1, or no, 0, or the person does not die, which is 1, or anyhow you switch it. So that's another behavior. So we have either death or alive. So that's another nature or behavior of a random variable. We have different kinds of behavior, like maybe you are buying something, maybe you want to withdraw in the ATM and you follow a queue. That is also a behavior of an event. So we look at how that event behaves. Oftentimes we use the Poisson distribution to characterize that behavior. Now, suppose that the only values a random variable x, say x, can take are x subscript 1, x subscript 2, up to x subscript n. Sorry for the error in notation here. It's supposed to be x subscript 1, x subscript 2, and so on, up to x subscript n. Now, this is the range of x. Okay, sorry. That is, the range of x is the set of n values. That is x1, or either event x1, or event x subscript 2, or event x subscript n. Now, since we can list all possible values, this random variable x must be discrete because it is countable. Remember, when we're defining a discrete random variable, we say it is finite or countable. Now, then the behavior of this random variable is completely described by giving the probabilities of all relevant events. So let's look at a mathematical notation to give us more mathematical clarity. Now, event, we have by this side, we have event, and then by the right hand side, we have the probability. So if the event here is x1, then the probability of that random variable is equal to x1. If the event is x2, if the event is x2, sorry, then the probability here is x equal to x2, and so on and so forth up to xn. So in other words, we specify the function probability of x equal to x for all values x in the range of x. So this like a more explanation to the discrete random variable. Now definition. So we want to define the probability function of a discrete random variable or a probability distribution function. Sometimes we say PMF. For a discrete distribution, we use PMF to connote probability distribution function for a discrete random variable. Now, the probability function of a discrete random variable x is the function p of x satisfying uh, what we have here. So probability of x equal to probability of x is equal to x is discrete. So for all values x in the range of x, so we use pf as an abbreviation for the probability function of a discrete random variable, or otherwise we use PMF sometimes. Notation. So anywhere we see this notation, p of x, small letter p of x, or p subscript capital letter x of x, we use that to denote the probability function of a discrete random variable. So we use the px of x form when we need to make the identity of the random variable clear, so that when we see this, we know that we are talking about the probability function of a discrete random variable. Now, in practice, the PF, the PF is sometimes given the alternative name of probability mass function, or PMF. So anywhere we see PMF, we're talking about the probability function of a discrete random variable. An example, let the probability of a head on any toss of a particular coin be P. From independent successive tosses of the coin, we record the number x of tails before the first head happens. Remember, we define independent events as the event of occurrence of one not affecting the occurrence of the other. So in the case of the toss of a coin, if head occurs, uh, then it will head will not occur. And if head occur, then the tail, sorry. If tail occur, then the head will not occur. And if the head occur, the tail will not occur. Now, range of x. Remember we define range of x. You see the range of x is the sample space of the discrete random variable. So the range of x in that toss will be 0, 1, 2 continually. And the probability of x equal to 0 is equal to p. Then the probability of x equal to 1 is equal to 1 minus p times p. P is the probability that we're looking for. Then 1 minus p is the probability that that event, uh, the negation of the event continually up to probability of x given small x equal to 1 minus probability of. So let's take note of some of these mathematical notations. The probability function for the random variable x gives a convenient summary of its behavior. The probability function is given by p of x, px of x is equal to 1 minus p up to the raised to the power of x times p. X equals to 0, 1, 2 continually. So x, using this probability mass function, this we can say that this random variable is said to have a geometric distribution. So this is the probability mass function of a geometric distribution. So as we go on, we will see more and more for other distributions. And the geometric distribution is a discrete probability function. So when we go deeper into this course, we'll be able to see all the distributions that are categorized under the discrete random variable or discrete probability distributions, and then we'll see the ones that are categorized under the continuous probability distribution. Now, properties of a discrete probability function. Now, if px of x is the probability function of a random variable x, then px of x is greater or equal to 0. Like we have explained here, one of these axioms of probability, which means that it is non-negative. So we're saying for all x in the range of x. Now, though this may sound somehow abstract or mathematical, but I believe as we delve more and more and we start taking more examples, we will get a clearer understanding of all these behaviors. And then also, uh, when we take the sum of a of the when we take the sum of the mass function is equal to 1. Remember that axiom of probability, the probability of union when we explained earlier on. So here, where the sum is taken over the range of x. Now, an informal definition of a distribution. The probability function of a discrete random variable describes how the total probability, 1, is split. Remember, the total probability is 1. I've explained that as one of those axioms. Is split or distributed between the various possible values of x. So informally, we can define a distribution that's a discrete random variable as. Now, this split or pattern is known as the distribution of the random variable. Now, let's note the probability function is not the only way of describing the distribution of discrete random variable. So there are other ways of describing the distribution of a discrete random variable. and any one-to-one function or the probability function will do. But in for this lecture, we are or this class, we are only interested in the distribution of the random variable and not the other functions that may describe its behavior. Our definition, the cumulative distribution function. So there are two things we should note under probability distribution function. One, the probability function, or otherwise called the PMF. Then two, the cumulative distribution function. From cumulative, we understand what it means. It means we are taking the sum of all possible probabilities, we're summing all of them cumulatively. So the cumulative distribution function of a random variable x is the function f sub x, capital letter X of x. Remember, for that of uh, remember for that of probability function, this we use this here, p subscript capital letter X of x. But for the cumulative distribution function, we are using capital letter F subscript capital letter X of x, what we have here. So anywhere we see this, we know that we're talking about cumulative distribution function. Whereas anywhere we see this, we know that we're talking about the probability mass function. So we use this throughout, even when we're talking about our continuous probability distributions. Now, we see that the cumulative distribution function of a random variable x is the function f of x, fx of x is given by this expression. So we have uh, the cumulative distribution function is equal to the probability that uh, the random variable is less than or equal to the probability x here. So but it's like, in other words, we're saying we're taking the the sum of all the possible probabilities for all values of x in the range of x. Now, so this is the abbreviation. We use CDF to abbreviate cumulative distribution function. And then the terminology. The CDF is sometimes given the alternative name of distribution function. All right, Mrs. Ebun, please.
Okay. Sorry to interrupt. I have to quickly go somewhere, and I'm sorry because of attendance. That's why I'm taking permission so that you know that I didn't just leave the class. Sorry about that. And I don't know if I will
Okay.
the class again.
All right. So
Yeah.
you'll be back when?
I don't know if I can meet the class. I need to get somewhere immediately now.
Okay, it's all right.
Yeah.
It's
Sorry
okay.
about that.
No,
I hope
wahala.
it's recorded, so I'll
Yeah,
change
it's
it.
record. It
Thank you
is.
very much.
Yeah, you're welcome.
Okay.
So can we continue? Mr. Osaho, are you there?
Sure, I'm here.
All right. So let's go ahead then. So we say it is abbreviated CDF, and then the terminology. The CDF is sometimes given the alternative name of distribution function. Notation. We use capital F of x here to represent cumulative distribution function, or we use capital F subscript capital X of small letter x to denote the cumulative distribution function. So we use this form when we need to make the identity of the random variable clear. So what is the relationship with probability function? Now for a discrete random variable, if we're looking for the cumulative distribution function, remember we say it is the cumulative of all the probabilities. So we take the sum as we have here, we take the sum of all the probabilities of that event. So that is for a discrete random variable, we take the sum. So we use this expression for that. So as we go deeper, we will understand more and more how we go about this. Now, example, if a random variable has range, has this range 0, 1 up to continuously. Now, the cumulative function, that's for the f of x, fx of 3 is equal to the probability that the event is 0 plus the probability that the event is 1 plus the probability that the event is 2 plus the probability that the event is 3. So we're summing everything. So that will give us the cumulative distribution of the third event. And also the probability mass function. So you see we are giving some difference here. The probability mass function that the event is 2 is equal to the cumulative distribution function of 2 minus the cumulative distribution function 1 here, as we can see. Now, properties of CDFs. These are some of the properties of our cumulative distribution functions. So now, anywhere we say CDFs, we're talking about CDF or CDFs, we're talking about the cumulative distribution function, or simply put, the distribution function. So we say 1, all CDFs are monotonic non-decreasing, or we can say they are monotonic increasing. Monotonic non-decreasing or monotonic increasing means that they are continually increasing. They may not necessarily be increasing always, but they can never come backward, which means once they increase, they can either be that value or the at. So they are monotonic non-decreasing. That is what it means. It does not mean that it's increasing continually. It may remain where it is, but it can never go back to, it can never reduce or that's decrease. So it's always increasing. Now, secondly, all CDFs satisfy f of x of negative infinity is equal to 0. We know that we have positive infinity and negative infinity. So negative infinity, that's when we take the probability and the other, the negation of the probability countless times. We have 0. Now also, all CDFs satisfy also this function that we have here. So if we take the cumulative distribution function of infinity is equal to 1, that's the total probabilities. Any function satisfying these conditions can be a CDF. So any function that satisfies all these three conditions can be a CDF. So if we when you go deeper into probability distribution theory, maybe you are trying to get a new distribution, you must ensure for it to be a valid CDF, it must satisfy these three axioms or these three conditions. Maybe as time goes on, we will take a look at how we can be able to test these conditions. Any function satisfying these conditions can be a CDF. A function not satisfying these conditions cannot be a CDF. So even if the function invalidates one of these conditions, then it is not a valid CDF. Now, for a discrete random variable, the CDF is always a step function. It's always a step function. Now, let's be reminded, properties of CDFs. Any function satisfying the following conditions can be a valid CDF. 1, it is monotonic, non-decreasing. 2, it satisfies this condition. And then 3, it also satisfies this condition that we have here. So far so good. Is there any question concerning a random variable or any addition? Mr. Ilyas, you are welcome. So far so good. Is there any, do you wish to throw more light concerning what we've talked about on random variables and probability distribution? Okay, let's go ahead. Mean and variance. So the probability functions gives a complete description of the behavior of a discrete random variable. In practice, we often want a more concise description of this behavior. We want a more concise description of this behavior. And how do we do that? We can only do that by getting the mean, or otherwise called expectation, and then the variance of this random variable. Now, the mean or expectation of a discrete random variable x, denoted by e of x. So anywhere we see e of x, we're talking about the mean of a random variable or the expectation of a random variable. Remember, we say capital letter X stands for variable, random variable, and then when we see capital letter E of x, we're talking about the expectation of a random variable or the mean. So the mean is also the expectation of a random variable. It's defined as expectation of x is equal to the sum of the summation of the x times the probability of random variable x equals x. So once we take this function, when we start taking some examples, we'll see how we can actually use this mathematical notation so that it will make more meaning when we're looking for the expectation of the random variable. So note here uh, and later the notation summation here, this notation here means the sum over all values x in the range of x. So when we see this notation, this sigma, and then we have x under, it means the sum over all values x in the range of x. So the expectation here is a weighted average of these values. It's a weightage uh, is a weighted average of these values. The weight always sum to 1. So the extension. The concept of expectation can be generalized. We can define the expectation of any function of a random variable. So thus, we obtain for a function g of x of a discrete random variable x. So expectation of g of x is given by the expression down here. So measures of variability. So two random variables can have equal means, but very different patterns of variability. So here is a sketch. For instance, we have a random variable that has the same mean, but when we look at this graph here, we see that they actually vary. The variability varies, but the mean might be the same. So to be able to distinguish this, we use the measures of dispersion. We use the dispersion, which is also the variance or standard deviation. So measures of dispersion. There are many possible measures. We look briefly at three possible ones. One, the mean difference. Uh, so this is the mean difference, the expectation of a mean difference, given by this expression. Then we also have the mean absolute difference, given by this expression. The only difference is this absolute value here that we have. Then also we have the variance, given by this expression. The variance actually means the sums of the deviation, the sums of squares of the deviation from the mean, which is the most frequently used measures. So the notation for the variance is given by this v of x, or when we see variance of x, we mean the variance of x. And here we have the variance of x to be given by this expression. Now, summary and formula. In summary, the most important features of a distribution are its location and dispersion. The location, which is the mean, and then the dispersion is the variance, and then the standard deviation, which is the expectation and the variance. We see that the mean is the expectation and then the variance. So the expectation for a discrete random variable is given by this expression here, this expression, and we use mu to represent that, whereas the variance is given by this expression here. So when you look at this expansion here, you see that it gives us uh, this formula here. So remember, we see that the notation this means the sum over all values of x in the range of x. So we can also denote the expectation or the mean by mu, and then we denote the variance by sigma squared. So example, we find the mean and variance for the random variable x with probability function as in the table below. So given that we have this value and the respective probabilities, let's say for 1, the probability is 0.1, for 2, for event 2, the probability is 0.1, for event 3, the probability is 0.2, for event 4, the probability is 0.4, for event 5, the probability is 0.2. So the expectation of x given by this formula will be this. So uh, now clearly we understand what we mean by all those formula that we're writing there. So it means you take uh, from our formula for expectation here, we see the summation of the x. Oh, sorry about that. I'm experiencing a network glitch. Sorry, let me sort it out. I'll be online. As soon as possible. Hello everyone.
Hi.
Hello.
Sorry, I think I had an issue, power outage. So I don't know how we're going to do this. Um, my sharing may no longer share. So I think if you can just give me like 5 minutes, I'll share the file to Sharabil, and then he'll help me and project from his end. Is that okay?
All right, no problem, sir.
All right. Thank you. Can you see my screen? Hello, can you all see my screen?
Yeah, yeah.
Yes, yes, yeah.
All right, thank you. Okay, so sorry for the breaking transmission. So back to our example, we we say that looking at this the data we have in this example, we want to find the expectation of the random variable given in the table. So using our formula for random variable, we say it is the sum of x over all the random variable multiplied by the probability of the given uh, event or this event. So our expectation of x or the mean becomes 1. We see that the random variable x here is 1. The value of x here is 1 times the probability, which is 0.1, plus, because we see it is the sum of the sum. So we're summing the product or the probability and then the value. So we have 1 times 0.1 plus 2 times 0.1 plus 3 times 0.2 continually up to 5 times 0.2. So the, the expectation or the mean of this random variable as provided in the table above is 3.5. So whereas the variance, uh, if we expand the formula for the variance of a random variable, just like we did above here, we see that we have expectation of x squared minus the square, the squared of expectation of x. So if we expand that and using that formula, we can now find the value of the variance of x. So using the formula, we have the expectation of the x squared. So we squared all the individual random variables times the respective probabilities. So we start for the first one, 1 squared times 0.1 plus 2 squared times 0.1, which is the probability of the random variable 2, plus 3 squared times 0.2. Continually, if we do that and we sum all of them, we get 13.7, which is the variance of which is the expectation of the square of the random variables. Then when we now find the expectation of the variable all squared, because there's a difference between the first expectation and the second expectation. The first one here gives us the expectation of the square of each of them, whereas the second one here gives us the square of the expectation. So we already got obtained the expectation here as 3.5, so we just square it. So we have 13.7 minus the square of 3.5, so which gives us 1.45. So now we can understand the dispersion of this particular of the data in the table above. And then we know that the standard deviation is the standard deviation is the square root of the variance. So from our variance here, we just take the square root and we have our standard deviation to be 1.20. Now, the concept of expectation of variance apply equally to discrete. That's in summary, the concept of expectation and variance apply equally to discrete and continuous random variables. So in our next class, we'll check more on continuous random variables and we'll see some few examples on some of the properties of the uh, CDF and then EPDF. Um, the formula given here relate to discrete random variables. Formula need slight adaptation for the continuous case. So for the continuous case, we'll vary them small, we'll just give some small slight adaptation so that it will be able to adapt to the continuous case. Then 2 units. The mean is in the same units as x, which is the random variable. The variance, that's the variance of the random variable defined as variance of x is equal to the expectation of x minus the expectation of x all squared. It's in squared units. Now, a measure of dispersion in the same units as x is the standard deviation, which we know as the square root of the variance. Now, lesson summary. Now, in the beginning, we explain the conditional probability and the Bayes theorem. We said that the conditional probability is when we're looking for a probability distribution, the probability of an event, given that there's an additional information. And we say that the Bayes theorem or the Bayes rule is another excellent formula that will enable us to obtain such situation. Now we look at the Bayes theorem, and then we explain the Bayes theorem. We got the formula for the Bayes rule, and we're able to solve a simple example on the Bayes theorem. We also talk about the random variables, and we explain random variable as an event happen randomly, and because we don't know the value it may take, the numerical value it may take, we say we can call it a random variable. And we say that a random variable is denoted by RV, or when we see capital letter X, it stands for random variable. And we say that sometimes because we find it difficult to characterize the behaviors of this random variable, the probability distribution helps us to understand the behavior of this random variable. And under probability distribution, we see that we have the discrete probability distribution, which is probability distribution of a finite or countable events for random variables. And then we also say there is the continuous probability distribution, which is the probability distribution of a continuous value. And we say that in practice, when we say a discrete probability distribution, we actually mean a random variable that takes a value that does not have a decimal place. Let's say 1, 2, 30, 50, 200, and so on and so forth. And then when we say continuous, we mean events that takes, let's say, maybe a decimal point like 2.5, 1.0, 0 point something. Insofar as there's point, we say that they are continuous distribution functions. Now, we also explain what a probability function is, and then we also explain the cumulative distribution function. Now, we see for the probability function, it is denoted by small p subscript capital letter X of X, and also see for the cumulative distribution function is denoted by capital letter F of X. We also explain the mean or the expectation of a random variable and the variance of a random variable. Now, exercises. So this exercise was the one we gave earlier on. So we are going to solve this particular exercise with the next one in our and present in the next class. We actually give two exercises for this particular today in this lecture today, in this lesson today. We give two exercises. We see that these two exercises, they are going to be done and presented by us in our next class, that's next week, and they are going to be graded. So we say we are going to give some few moments for people to present the exercises before we continue the next class, and then we'll grade them. Now, in our next class, we will talk about moment generating functions, their properties, and their uses. And then we'll also look at the discrete probability distributions, some discrete probability distributions. They're actually numerous, but we'll look at some. We have the Bernoulli distribution, we have the binomial distribution, we have the Poisson distribution, the geometric distribution, and the negative binomial distribution. These are some of the distributions discrete probability distributions we'll be looking at in our next class. Then when we are done with the discrete probability distributions, and under this we'll be looking at their probability mass function and their continuous distribution function. And then we'll also be looking at how to get the expectations, and then also their variance. Then we'll try and do that for each of the distribution, and then we'll look at some examples how we apply in actuary. In actuary, in insurance, we'll take some examples how they apply in actuary, and then we'll be able to solve them. Thank you for listening. God bless you. So we have come to the end of the class. So at this juncture, before we ask some questions, I would like to give Ilyasu the opportunity to maybe say one or two things or to summarize to shed more light on what we have discussed so far in today's class. Ilyasu, are you there?
Yes, I'm here. And thank you for delivering this class, and thank you everyone for joining. Maybe do we have any question or something is not very clear? Yeah, so you can ask. Let's just quickly wrap up the call because I can see we have just 30 minutes to end the class. Just to check your understanding, I mean, I see that today we discuss more on discrete and continuous. This is very, very important because by the time we start pricing insurance products, these are the things we put into consideration. And when you are talking about probability distribution in general, there are two, discrete or continuous. So when I'm talking about continuous but and discrete here, I'm specific about the random variables x. So um, we have I believe we have understanding of claim amount, random variable. Let's say for someone that buy insurance policy, that the payment is at the beginning, at the moment of death. At the moment of death, it's an insurance policy you buy. Doesn't matter, term insurance, whole life insurance, but then the payment is the benefit is paid at the moment of death. Like if you die today, you get the benefit paid like at that moment. And then another example is payment at the end of the year of death. For example, you buy the insurance policy in January this year, 2024, and then you die within this year, but you will not get the payment at the moment of death. You get at the end of the year of death. For example, it will be, let's say, in December, if you are using the calendar that way. So can you tell me which of this contract, the claim, the random variable, the claim amount is discrete, and which one is continuous? Any ideas? Okay, so it's okay. I can understand it's very late to ask this question, but it's just to check our understanding. Yeah, so please find out. This one, remember,
Or maybe you can throw the question again or put it in writing. Then by next class, maybe they will brainstorm and then they will come with the answers.
yeah, I mean, this is just for practical example purposes. It's easy. This payment is done at the end of the year
Sorry.
of the.
Hello.
Yes,
Sorry, my apology.
no problem.
Because I am still in the office and I have
Yeah.
my colleagues that were, so I think I missed the question, but I
Uh-huh.
wouldn't ask that you repeat yourself.
Yeah.
Maybe as suggested by Shahabil, it
Mm-hmm.
could be put in writing and
Yeah.
thrown at us. Yes.
Yeah,
Sorry
sure.
for
No problem. But maybe Mr. Osahon know this answer. The insurance
So
policy.
sorry. I was also I because I'm actually using my phone
Ah, okay.
to connect. So a
Mm-hmm.
call came in which disrupted my
Yeah,
connection.
yeah. Got it.
So yeah. Thank you.
Yeah, okay. So the question is the insurance policy payable at the moment of death. So the claim random variable in this kind of policy, is it continuous or is discrete? And then the insurance policy that is payable at the end of the year of death. The claim random variable here, is it continuous or discrete? Yes. Go ahead, Mr. Bello.
Okay, thank you. I think the one that is payable uh, on debt, um, I will vote for that as being continuous because
At the
any
moment, yeah?
yes, yeah, because that debt can happen at any time,
Yeah,
which is going to be like a fraction of a year.
yeah,
But the one that is payable at the end of the year,
yeah.
I would take that as discrete because that
Thank
is
you
a
so
whole
much
year.
for this
Thank you.
answer. This is very correct. And that is it, just to see the real life application of what we are doing. So this random variable, the claim amount random variable, The payment is at the moment of death, so it's continuous. Yeah, and then when it is at the end of the year of death, it's fixed. Even if you die in January, the insurance policy you will not get the benefit until the end of the year of death. And thank you very much for this answer. So that is all from me. And yeah, have a nice evening. I'll just drop. Or if there's any comment or observation, please feel free to
All
give
right,
us.
yeah, Elias, we thank you for that practical chipping. Is very, very insightful and thoughtful.
Yeah.
I believe it will give more insight to what we have been doing, which seems somehow abstract. So
Yeah.
yes. So now I don't know if there is there any other question.
Yeah, I also want to look at the question now,
Yeah.
um, so that to have more understanding. When you
Yeah.
say discrete, are we not referring to the value that is an integer? And
Yes.
when you say it's continuous,
Mm-hmm.
so insurance claim for at maturity to be
Mm-hmm.
something that is known by both the assured and the insured.
Yeah.
Sorry, by the insurers and the assured. In my own opinion, it should be um, a discrete. It should be a figure that is already agreed on. I don't
Yeah.
know whether I'm
So
making a
when
point
we
now.
say discrete
Yeah.
here, we are talking, what we are talking about in general is the random variable, the claim amount.
Okay.
This like the
Okay.
money
Yeah.
that the benefit that you will get. So
Yes.
yeah, the first example is that insurance policy payable at the moment of death. Like you buy this insurance policy, the claim amount will be paid
Okay.
at the moment of death.
That's
So is it,
when you die, they pay.
yeah, yeah. So is this claim random variable discrete or continuous? And the second is that the insurance policy payable at the end of the year of death. So is this a random variable discrete or continuous? So Osahan, that's the question here. So we are talking about
Okay.
both of them are values. Both of them, whether it is discrete or continuous, insurance benefit is a value. But when
Exactly.
something that has interval, is discrete, and we model it using discrete continuous,
Okay. Okay.
sorry,
Okay.
continuous
All right.
probability distribution. Yeah, that is just what we
Okay.
mean. You can read more on
Okay.
this. Yeah, because it's very, very
Okay.
important when it's come to pricing. Even I had you mentioned earlier you do more of underwriting, so it's very important to understand when you are writing the insurance policy. When is the payment? Is it at the moment of death or at the end of the year of death? We will do all these things, like yeah, pure endowment and all those stuff related
Okay.
to
All right.
insurance. Thank you very
Thank you
much
very much.
for asking the question. All right, so thank you all, and bye.
All right. So let's all have a good night. So let's try and we'll send the assignment at the learning. We'll put the assignment clearly at the learning LMS, and then also put it in the drive. So let's try and get the assignment done, and then we'll present by the next class. It will also form part of our continuous assessment. So let's all have a good night and have a great